Hello everybody, thanks for the invitation to speak here. The background's been set up perfectly for me by Yujang to talk about epilepsy and by Martijn to talk about connectomics. So I'll skip most of this except just to say that hopefully you're convinced by now that epilepsy is a real societal problem. There's a lot of patients with epilepsy and it's a major economic burden amongst other reasons why it's a bad thing. So focal seizures are a particular type of seizures. Focal epilepsy is a particular type of epilepsy. And patients with focal epilepsy have seizures which are essentially mainly constrained to just a part of the brain, just an epileptic focus. And the long-standing thought was that this is caused by focal abnormalities to the brain tissue. And in many cases, this is the truth. So it can be caused by a brain tumor, for example, just a focal part of the brain, abnormal tissue, and this can lead to focal seizures that are spatially constrained in their onset. However, recent literature has suggested that it's actually a bit more complicated than this, and that epilepsy is an emergent phenomenon of abnormal networks, which are more widespread than just the observed seizure focus, which is spatially constrained. And so there's been lots of literature lately saying that these abnormal networks can be what's leading to the seizures. So in this talk, I'm going to talk about structural networks, and in particular structural networks inferred by diffusion tensor imaging. So quick summary of what I mean by this. So what we can do is we can infer network nodes using a parcellation scheme here, and that can be obtained from parcellation of the structural T1 image. And we can also infer connections between those nodes using diffusion tractography from a diffusion image. These two can be registered to the same space, and then connections between one node and another can be inferred, and we can generate a connection matrix, something like this, where we have nodes and connections between them, and these can be represented in a matrix. One thing you'll notice is that not all nodes are the same. So here's the superior frontal gyrus, so this is a very large node, and at the front here you've got the temporal pole, which is one of the smallest nodes. And so to make fair comparisons, it's not quite so easy. So we have different nodal properties, and we have also different edge properties, so connections. So there's different ways in which we can define the edge in the network or the connection in the network. This can be done by connection weight, which is kind of normalizing between the density of streamlines, which takes into account the node size and the number of streamlines connecting. Or we can just use the number of streamlines, which is done in a lot of studies, or the length of the streamlines. There's any number of ways that you can use to define your edge strength, if you like. And what a lot of studies do is they take this weighted connection matrix, they set a threshold, and then binarize it. But all of these lie around the assumption that edge weight or strength or a weighted measure is representative of what's underneath it, what's going on. And as you saw in the previous slide, many studies have shown that there's alterations in these edge strengths or these connectivities between patients and controls. And my question here that I'm trying to investigate is, what's driving this? Is it alterations in the grey matter node size? Or is it alterations in this white matter connectivity? Or is it a combination of both? So just as I've said that all nodes are not equal, some are bigger than others, all nodes that are the same node in different subjects can also be different. So the same node can be bigger in one subject than another. And this can also influence the connectivity. So I'm interested in finding out what's driving these network changes that have been found in the literature. So we begin by just looking at the node size. So in this case, we've looked at the surface area of each of the 82 nodes in this case, picked a widely used parcellation scheme, the Desikan-Kileni free surfer parcellation scheme. And we've looked at 22 patients with temporal lobe epilepsy, so focal epilepsy thought to be constrained to the left temporal lobe, and 39 age and gender matched controls. And we essentially just plot the t-statistics, or how far apart these two distributions are, for each of the different regions. And we see widespread atrophy in pretty much the whole brain, and this is because patients have smaller brains than controls in terms of the total surface area. This has been reported before in literature, this is not particularly new. We've known this since probably the late 80s when early MRI studies were done in this. But it's just important to highlight this, the fact that there are differences in nodal properties in patients that may be driving the connectivity changes that's seen in previous studies. So what about if we just look at the connectivity values? So we can look at the number of streamlines as a measure, as is done in many studies, And here we look at the, so this is a t-statistic of each of the edges in the network. And you can see it follows a pretty normal distribution. There's no huge outliers here on either side. If you were to plot this equivalent distribution for the surface areas, it would have been very skewed to the left because they were shrinked a lot smaller in patients. And when we plot the top 10% of these, just an arbitrary number, we can see that there is no obvious spatial profile to the left hemisphere, as we may expect, and these are not significant after correction for false discovery rates or multiple comparisons. And so using this measure of just the number of streamlines, the connectivity is actually not different, really, I would say, having seen this. What we can do is look at a different measure that's widely used in the literature, and this is the connectivity weight. And many of you will be familiar with this study, I would expect. Yes, no? It's one of the key studies that kick-started the whole structural connectomics revolution, if you like, that we've seen in the recent years. And it essentially takes a connectivity weight, which is a function of the density of the number of streamlines for the surface area, normalized by the length of the streamlines that interconnect those two areas. And Hagman used this in his study in healthy subjects, which I think is fine, there's nothing wrong with that. And I tried this in the patients to see if this would result in significant differences, and it does, even after FDR. And so we find that in a subset of the connections, there are, when using this measure, this definition of connectivity weight, as many studies do in the literature, we find these significant differences. But I would argue that these differences are actually really being driven by the alterations in the nodes in the network, rather than necessarily the connections between them. And so I would say if you're doing any connectomic studies, looking at differences between groups, so whether it's male or female, it's well known that females have smaller brains than men generally, or young and old, older people have thinner cortices than males, or disease cohorts where there's known differences. I would say one should really take this into account and at least be aware of this in any structural connectomic studies. So that's all well and good, but that doesn't really tell us anything useful for treating epilepsy clinically with consultant neurologists in the hospital. And I'd just like to draw your attention to this number that Yijang touched upon in her talk. So around 30 to 50% of patients who have focal epilepsy will go into surgery. They have their outcome is not good. So they will still have seizures even after having this invasive surgery to remove what is thought to be the epileptic causing part of the brain. And the reasons for this are not fully known, but it's been suggested in recent years that epilepsy is a dynamic disease. There's seizures come and go, seizures evolve over time. They may start off with fast oscillations or high amplitude spikes. They may come and go at different times of day. So some patients have more seizures during nighttime or different times of month. So I would argue that there's strong evidence to suggest that epilepsy is a dynamic disease in addition to aspects of structural properties of the brain, such as the network that was described in the earlier studies. And so if we take both of these aspects into account, the dynamics and the structure, the goal really is to ultimately see if we can predict surgical outcomes for patients before we do the operation, before we remove the part of the brain in this invasive clinical work that's done. So here we've used the same data, so 22 patients, and we've included the connectivity, so this is the connectivity matrix M, into the model with the realistic time delays. And we have essentially the model it exists in a bistable state. So there's a stable fixed point and an oscillatory limit cycle around it. And the likelihood of transiting from this state to the epileptiform state is dependent upon these parameters, which are inferred from the patient data. So M, which is the connectivity matrix, the delays, and also the degree of atrophy in the patients. And this is all node-specific and derived from the patient-specific data. And so the first thing we can do is simulate this model and see if it gives us something reasonable looking for a seizure. So here you've got a time series of a subset of the network nodes. So there's 8 nodes here overlaid on the brain. And when one goes into a seizure state, you'll see it pop up on the brain. So there's the first one, that's the left temporal, I think. And then we've got right thalamus popping up and others as the seizure spreads quickly throughout the brain. So that's great. We can simulate the seizure spreading in the patients. Can we predict the surgical success rates, or can we explain that? So, as I've said a few times, it ranges between 30 to 50% the success rate. The reason for this variance is, one of the reasons is because it depends on where the resection is. So if you have a temporal lobe seizure and you have surgery for that, it's probably going to be like 70%. If you have frontal lobe seizures, it's probably going to be more like 50%. So here we're only looking at temporal lobe patients, so we would expect the success rate to be about 70%. And here's the literature that explains all that. And we essentially asked the model, what happens if we remove those nodes from the network and re-simulate the model? Do we get an improvement in the seizure likelihood following that, that simulated resection? And if so, in how many patients do we see that significant improvement? And actually, in 72.7% of the simulated patients, we see that improvement. So we're matching the clinical data in two regards. First of all, the seizure spreading, and second of all, the success distribution, if you like. And the reason for that is this initiation at nodes with high atrophy and at network hubs, and the spreading through what we think are possibly healthy connections or normal connections. So the model can reproduce this essentially likelihood, this probability of having a successful outcome. What about individually? What about if we test this on individual patients? Can we predict their outcome? Well, this is preliminary work that's currently in review on two patients that I'm showing here. And patient A, we've plotted the simulated seizure likelihood. So which nodes go into that seizure state sooner than other nodes. And we've plotted this spatially, and the red nodes are the ones that go into the seizure state very quickly, using the patient data again, and on both panels. And the black nodes are those that were actually clinically resected. And you can see that in this patient, they overlap quite a lot, and in this patient, they don't. So the predictions from the model would be that this patient would have a very good outcome because you're essentially removing those nodes from the network that are causing the seizures. And in this patient, you would have a very poor outcome. And we went back to the data. We did this blind to the actual outcomes. And we went back to the data and we found that actually, yes, that patient does have a good outcome. And actually, that patient did have a poor outcome. They had seizures even after chopping out that part of the brain, as brutal as it sounds. And then we did this for another 16 patients. So we've got 18 patients in total, and we get 83% accuracy, which when you think that the clinicians only get around 70% accuracy, I think we're doing pretty well there. Importantly, probably one of the best figures from this is the 100% sensitivity. And what that means is that in all the patients where we predict there will be a bad outcome, they actually had a bad outcome. And that's crucial because that means then we can go on and say to the surgeon, here's what we think you should be doing instead. We think you should be operating on this part. And maybe the surgeon will take that into account and investigate that a little bit further. So to conclude, there's kind of two bits of work here that I presented, but I think the first bit is very important to bear in mind for many or most connectomic studies, is that especially if we know that there's differences in volumetric measurements or differences in surface area between subject groups, if you're doing a connectomic study comparing groups, I think that this is crucial, that these aspects should be considered, especially in these groups, for example, where we know there's differences. Dynamical simulations may be useful for providing mechanistic interpretation. So why are these seizures spreading in the model? Why are they spreading in the patients? And why might seizures come back? And accurate predictions are possible, and we can investigate alternative surgery strategies with these techniques. So with that, I'd like to thank Nishan and Francis, who were the students which did a lot of work on this. They were master's students with me in Singapore and in Newcastle. And I'll just do a shameless plug there for the conference that we're doing next year. Thank you for your attention. Thank you.
Rather than DTI-based structural connectivity, what do you see? Is that different, or does it slavishly follow structure?
So I skimmed over that very briefly. So this is actually using the functional connectivity between ECOG channels.
No, I meant fMRI functional connectivity.
I'd love to try it. So there's studies showing that there are differences between patients and controls in functional connectivity, as you might expect.
So sorry, but if you've got a large, I don't know, if you've got a data set of patients with resting state functional connectivity, and you've got the last 200 patients who failed, or you accumulate them from data sets across the world, you could ask the question where the local connectivity, it'll be something a lot coarser than you get from ECOG, but if you could get something, it would be very, very clinically useful.
Yeah, I agree, it could be useful. Typically, fMRI, resting state fMRI, is not clinically acquired, so getting that data would be a big challenge. A better option might be to do MEG, resting state MEG, and source localize that. So there was a paper out in Brain last year or the year before, I think it was Engelot, which looked at that. And he found similar things to us, actually, these kind of network changes that correlate with what are seizure foci in good outcome patients. Good idea. I think that's a way to take this, absolutely.
Okay.
Thank you.
Thank you very much.